So there has been talks about whether centralized banks are coming into blockchain or not, and whether people want to accept crypto. There is a one world where everyone wants to be decentralized, don't wants bank to enter the phase, and then there is the other part of the world who wants to control everything. But there's one common field where everyone are on the same page, that is a tokenization. If you see and go back to articles from 2024, and you will notice that many of the banks, like may it be McKinsey and Co, and not only banks, many of the big companies of the world, like consultancy companies, banks, McKinsey, BlackRock, and now HSBC, everyone has tried to step their way into tokenization. But is tokenization really secure? And if not, then how to keep tokenized assets safe in the quantum era? Let's try to understand this topic in our today's webinar. So, why should you care about quantum security, and why you should be, as a AI maximalist, thinkers from wizards, understand this and should care about it? So basically, digital, let's start to understand what is tokenization and what are the risks. And let's just try to get a little bit of story behind it. So digital ownership of assets like gold, real estates, or others is known as tokenizations. Now, to tokenize these assets rely on encryption to ensure the security. And this encryption is provided by various ways algorithms, which in today's method mostly are RSA or ECC, which is elliptic curve cryptography, but they are at the risk of getting decrypted due to advances in quantum computing, and it is as sooner than we really know, and it is advancing at a very faster pace than we expected it to be. So why you should really care about it? Because quantum computers soon are going to be powerful enough to break the current cryptography protections, which means that the hackers that want to break in the future, they are just starting right now. They are trying to store the encrypted data now, and then they're going to decrypt it later once they have their hands on enough into quantum computing. And if we think that hackers are not smart enough, well, we are at the wrong pace, because we know that the attack could take happen with a very long time. And if you have been following our webinars, I just recently explained about the attack which happened on the Bybit, and it was not just a month attack or a day attack. It took at least an year long, and it required a really big organization, like people say entire government of North Korea was involved. So if the quantum security is improving and if quantum computing is improving, there can be many big organizations can come out of it, some governments can do it, and you don't know, and we don't know that how much uh, threat it can be. So to understand why it is crucial and how it can affect the asset tokenization aspect of it, let's try to understand the foundation of the DLT, which is the distributed ledger technology. And in the very layman's and simple term, let me try to explain it, is that it is a peer-to-peer connection. That means that my ledger is going to be always updated, and it's updating peer-to-peer. And this peer-to-peer is used with the help of the encryption methods. In most cases, it is RSA. So how it works is that to add any data into my DLT, I'm going to initiate a transaction which is going to be then recorded across the distributed network using these cryptographic methods. And what's the issue in these methods? That these encryption methods are mathematical problems that are extremely difficult to solve for classical computers, but not for quantum computers. Why and how? Because these methods are, like for example, RSA right now largely depends itself on how hard it is to factorize a prime number. So that is the issue with the RSA, that it is now relying right now itself, like it is backing on the part that it is very difficult right now to break the prime number and generate a private key out from the public key. You can always go on the one step forward, like for example the encryption method, as we always say, it is one sided, it is append only, that you can only move forward, you cannot turn backward. But with the terms of quantum computers, you can create and you can break and you can get the factors of a very large prime numbers very easily. Usually in this case it is 256 bits long, and if you think 256 bit is not that high amount, just check it out. Just go into the Google and just try to give a prompt that give me an output of a 256-bit number, and you will realize it is a very long bit number. And then it will be easier for you to understand that it is relatively very harder, or might take thousands of years to break a single RSA. by a classical computer. But that is unlike the case of quantum computer, because the word quantum has just changed the whole meaning. And if the encryption is broken, the tokenized assets that are stored onto those DLTs could become vulnerable to theft or manipulation. So yes, it is a very very thing to ponder upon. And when the world right now who wants to tokenize the assets, we don't want to tokenize the assets for just 1 or 2 years. We want to make it quantumly secure. We want to make it securely for the future. We just don't want to look at 1 or 2 years of the future. We might want to see out there in the future that can make it more and more secure. Now let's understand how quantum computers break encryption. So classical computers, they leverage traditional binary bits, which is zeros and ones. Everything, all of the performance is happening in zeros and ones, whereas quantum computers on the other hand, they use qubits. Now what is these qubits? So qubits are kind of binaries, but they have a freedom to choose which binary they want to become. Now it is a very interesting, because this is how the data is stored, and this is the very basic unit of how quantum computer is storing data into it. See, the concept of understanding a data into 0 and 1 was so simple, but if we just think about it and understand the concept of qubits, it is in itself a very technically deep concept. And then we are just talking about if it can be used. Now understand, if a person that has ability to flip itself, like it has a switch that can toggle itself to behave at zeros and ones, and can it be used to break a thing which is statically 0 1? The answer is right there upon you. It can absolutely break that numbers. So that is the first advantage of the quantum computer, that it is using qubits, which means that it has ability to channel itself to behave at anything that it wants to be. It can behave at 0, at 1, or at any point of time. And then it uses superposition and entanglement for complex calculations, which helps it to become exponentially faster. And then it uses Shor's algorithm that can effectively break RSA encryption. Now, to give you a context, Shor's algorithm was given by Peter Shor. It is not very recent. It has been given by Peter Shor in 1994 itself. And since then, it has been a thing to, it has been a risk for the RSA that it can break RSA, but there was no computer powerful enough to use the Peter Shor's algorithm. And now, when we are seeing that, we have just now shifted, and I would say the world has shifted its power from classical computers to GPUs already. So it is not going to take much time to shift its power from GPUs to quantum computers. So now, once quantum computer reach a certain power level and become accessible enough, these DLT methods will be easily able to be broken down with the help of those. And RSA and ECC, which is elliptic cryptography, will no longer be secure and won't be relevant. So the solution is post-quantum cryptography. Now, post-quantum cryptography means a new encryption methods basically defined to and designed to withstand these quantum attacks. Because when we are trying to when one part of the world which is trying to bring out the quantum computing, the other part of the world are already working on to understand how to make it secure and secure for the attack. So now the PQC is being developed and standardized by NIST in collaboration with cryptography experts worldwide. So how does PQC works? It uses harder mathematical problems, which means that PQC algorithms uses lattice-based, hash-based, or multivariate polynomial problems that are resistant to quantum attacks. And then it is strengthening digital signatures, which means instead of using vulnerable cryptographic signatures, PQC creates quantum-safe digital signatures to verify the transactions. And then it is using secure data in the transit, which means a PQC that communication and asset transfers remain encrypted even in the post quantum world. And then is a gradual adoption and standardization, which means that the organizations must transition to PQC based encryption before quantum computers become widely accessible, which means that they need to act strong and they need to act fast. So the practical steps to make that quantum to tokenize SS quantum secure are a, upgrade first cryptography. The underlying cryptography should be upgraded like RSA and ECC with the PQC algorithms like dilithium 3, and use hybrid encryption for a smooth transition, which means that although it cannot be transitioned directly to the algorithms like lithium, because it won't be practical. As much as we say that transition that you can transition to it, but it cannot be. So right now the best opinion would be to use a hybrid encryption, which allows the flexibility of the current model to be entirely transmitted to a different model at the time when the quantum computing is at its peak, and then secure the DLT transition, which means that they deploy the post quantum cryptography's VPNs for encrypted transactions, and then use QRNGs for storing stronger cryptographic keys, and then upgrade the key exchange protocols. And at the last, we would say that the industry should adopt industry standards, which means follow the NIST PQC guidelines, implement government cybersecurity policies, and work with blockchain networks and regulators. Now, I would like to give out a shout out to the research paper by HSBC, which led us to create this webinar and understand how the how post quantum cryptography and could be used to make the tokenization most secure and have a good quantum secure field. So with this, we would like to end our webinar. And if you want to strengthen your security, we at the team's Token Minds have a security team which are doing this, are continuously working on it, and we are there to understand the security forefront, and we are out there on the web security as well. So do reach out to us and let's have a chat there. And if you want to know more about the latest advancement, you know what to do. You need to stay tuned, because we'll be back next week again with the latest cutting edge webinar again. Until then, see you. Bye bye. Be secure.